Good morning to everyone. This is the seminar number 14 of the year in this seminar series of the Magnetic Resonance Laboratory. We have an invited talk from Portugal that is going to be shared by Susana Cardoso de Freitas. So now I'm going to give a short introduction. Susana is graduated in technological physics engineering in 1996 and holds a PhD degree in physics from the University of Lisbon in 2002. In 2002, she was also a pre-professional engineer at IBM in the USA. After that, she became a researcher at the Institute and at Instituto de Ingeniería de Sistemas y Computadores, Microsistemas y Nanotecnologías, INESC-MN, and she is the co-leader of the Magnetics and Spintronic group since 2006. She was one of the team members awarded as second finalist for the European Descartes Prize for Research in 2004 for the work in magnetic memories for the future of nanoelectronics. Since then, she coordinated and participated as principal researcher in several European and national projects with a strong collaboration between the INESC-MN and the industry for advanced materials, device, and integrated system for robotics, biomedical, and industrial application. She's one of the directors at INESC-MN and an associated professor at the physics department, Instituto Superior Técnico de Lisbon, since 2015. And is responsible for student coordination and educational activities related with nanoelectronics, microfabrication, and spintronics. She was appointed coordinator of the educational activities of the IEEE Portugal section in 2015. Since 2019, she's one of the she's one member of the ambassador for the innovation group at EST. Susana also was recipient of the first place award in 2019 and an honorable mention in scientific award U Lisbon Santander in 2016, 17, and 18, and an award by the Magnetic Society of Japan in 2014. In 2018, she was selected as one of the 100 women in science by the Portuguese Agency of Science and Technology, Ciência Viva. In 2019, she was an associate member delegate to the European Physics Society Council, and in 2020 was elected member of the General Council of the European Magnetism Association, EMA, for 2021 to 2023. She has been invited for several international conferences and is co-author of over 300 publications and 20 chapter books. Her activities include intensive collaboration with industry, industrial partners for technology transfer related with sensors and for patents. And now she's going to enlighten us with a talk entitled Designing Magnetoresistive Sensors for the Integrated Solution with High Market Value. Please, Susana, you can go ahead. I stop sharing my screen.
So I must thank you for this intensive reading. It looks I'm an old person. I accumulate a lot of experience everywhere. So this is really, when we look back in time, it looks like the time has passed so fast since I was myself a PhD student. It was amazing. Okay, good. So I think now you should be seeing my first slide.
Yes.
Okay.
Yes.
Can you see it? Okay. Okay, very good. So I'm going to talk to you about my extensive experience. I'm not going to recall the dates for my PhD, so it was a long time ago. We work always in person. There was no Zoom or Teams, so the life was really more hard for the collaborations because we need to move ourselves and not use the digital tools to help us in these collaborative works. Anyway, I have been focusing my attention since I graduated. I focused my attention mostly in magnetic sensors, and it was not a passion choice. I just started with something, so I started doing my master thesis in magnetic characterization, magnetic material characterization, and then one thing brought to the other, and I ended up a few years later with several accumulated hours of, of work in a clean room related with magnetic thin films, and then using this to produce applications for this sensor. So this is something that I try to cover here with my talk. So very briefly, I'm not quite sure what is the background that the students that are listening have, but just a brief comment that spintronics is a word that presently pops up when you search for state-of-the-art magnetic materials and magnetic applications. And actually magnetism and spintronics are pretty much related. And spintronics is a concept that mimics the electronics, which is the conduction of electrons. Here is again the conduction of electrons, but we don't merge all these electrons in the conductive film as in copper, for example. In spintronics, we try to classify these electrons using their spin. So spin up, spin down. So we have two states. And if we have a ferromagnetic film as a conductive material, we can bring the electronics into a different level and can use the concept that was brightly described by Albert Fer and Peter Grunberg, and they were clever in working on the models for physics and then experimental results here, trying to see that in a conductive material, we have two channels competing for the conductive properties of the material. If it is a metal, we have the conduction for the spin up electrons and spin down electrons. And then the polarization is the contrast between these two populations of electrons that appears in the material. So this is not new, but presently we call it spintronics, but in the past we call it only magnetism and advanced magnetism. Now it's more sexy to call it spintronics, and we use it in the most modern devices and the state of the art. And this is mostly what is around my presentation today, is to discuss how these spintronic materials and the conduction in thin films, magnetic thin films, can be used for applications. And the basic component is what we call a magnetic tunnel junction here, where we have two metals separated by a oxide barrier. So it means that the conduction between the two metals will occur if there are the sufficient conditions from quantum mechanics for the electrons to cross across through the tunnel barrier. So this has been of high impact since 1996, 1997, although the spintronics have been discovered and projected since 1970. The impact of this, of course, it was more relevant in the early 2000s. And in that period, it was a very exciting area where we have the hard disks and magnetic storage information was still growing and gaining a large share in the market. And then this concept was awarded with Nobel Prize in 2008 in a very convenient time where most of the groups in Europe and through the world were already familiar with the thin films and nanoelectronics to read out these devices. So this is a brief graphic that highlights how relevant these technologies have been evolving with time. So if you look, when I started my PhD, was here in 1996. The heads that we have in our computers were inductive heads, so everything large. And we started to work on GMR. Actually, my PhD started to be on GMR. And then later on, I worked on TMR, and now we work on TMR and perpendicular materials as well. And during this period, this past 25 years or even more, what has changed is the density of information that could be stored, but also could be read, because we could store bits at atomic size, but then we cannot read them if we don't have sensors. So here the sensor has been a key factor for this information. And how important is the areal density? If you have low area density, means that if you want to write a lot of information, you need big computers like those that we see here. But then with time, everything starts to be smaller. So the density of information is smaller and smaller, and we could have more portable and more tiny components. So this is actually all about the shrinking of information and controlling magnetism of sensors and information, magnetic information stored at a nanometric scale. So what are the requirements here? And this is actually what I have been covering in the past years, and I'm going to show here through my presentation here and there. First, we have to have a good control on the material. So we should have good materials. We should be able to simulate those materials under realistic scenario. Actually, I could say that both of these tools exist widely, so we have very good online and freeware programs that enable us to do micromagnetic simulations in realistic conditions. We have very good deposition tools that enables us to grow high quality, good interface, atomic level control layers. Also, we can deposit at wafer level, so we can do more than 1, 2, or 30,000 sensors in a row, and we are able to integrate them in a visible external electronics that can be handled by our electrical engineers or somebody else. So everything here, it covers the integration, fabrication, but all starts with a common mode. So it's important to control the physics. So because if we don't understand the physics, then we are just users of the sensor. So this is actually what pays more. Regarding the physics, there is a lot of hidden information in the materials selection and in the control of the physics at unpatterned scale. So understanding the physics mechanisms. And I would say that after 20 years, there was a large evolution in the requirements in the market for this knowledge. So when I was doing my PhD, so late 90s, early 2000, there was a high request in the industry for people like me that were expert in doing thin film deposition. So industry could hire all students like me that could travel to Japan, to Malaysia, to United States, where the big companies had deposition tools. And so the industry absorbed a lot of younger researchers and young students for the deposition part. Then 20 years later, we saw that during these 20 years there was a large decay, so there is not a very interesting search for these profiles in the industry. Now, again, the industry are hiring people with expertise in thin film materials and optimization of the properties from the atomic level scale. So this is, again, a market that is hiring, and I can tell that industry is always trying to hire my own students. So I can tell this by true experience in the field. So what do we need to make a functional, interesting magnetoresistive sensor? So I call it here XMR sensors, and this is a common way to classify the magnetoresistive sensors, because there were several families of magnetoresistive sensors, as I showed you before. We have anisotropic, we have a giant, we have colossal magnetoresistance, we have tunnel magnetoresistance. So there are several flavors that were used depending on the material characteristics and on the level of magnetoresistance that we could extract from this sensor. So basically the two separation between the high resistance and the low resistance states. So generically I will call it XMR, and I will focus in 2 or 3 flavors of those. But essentially there is a large knowledge that is behind the designing of the sensors. And why do we need these sensors? What is the common mode for these sensors? They should have, and this is a common transversal to all applications, we want them to have a good spatial resolution. So the sensors are micrometric. So it's essential that we keep the micrometric dimension if we want to use them in fields. So we don't want millimeter sensors. We want to make profit of the nano size and the micrometric size. Again, also a very important feature here is room temperature operation. So this, even if it is tunneling effect, they should operate at room temperature, because the products in the market, and they can range from current sensors in the air conditioners, can range from ABS sensors in the car, automotive cars, can range from magnetometers in the satellites. So all this requires operation at room temperature. So this is quite relevant that we maintain this operation. Another thing is we want low price, and everybody wants low price. So large scale integration is an issue that needs to be considered. So if the technologies are excellent, but then cannot be scalable up to a few millions per month in a big foundry, then it starts not to be so interesting for the industry partners. And then again, versatile magnetic field detectivity. So this is a very fancy way to say that we want to be able to tune the detectivity. If you want to design a sensor that is sensitive for millitesla fields, then we should be able to design it for the millitesla. If you want to have it for femtotesla or for picotesla, then we should be able to know what to change if we want to target the end detectivity for those ranges of fields. So essentially, I'm going to focus on two different families, very popular, both of them. So this is a typical structure for GMR, so giant magnetoresistive effect devices. So it's a two-terminal, typically it's a two-terminal contact in plane current. So the current flows in the plane between the two or the four contacts. Commonly is also used to be named a spin valve. Is a valve that selects the spin. So it is a very interesting concept that Bernard Denis in France introduced here. So here internally in my lab, we always use spin valves. And the structure of these spin valves is comprised, so you should look always here, the spacer, the copper spacer, a few nanometer, 1 to 2 nanometer thick. And then on either side of the spacer, we have a ferromagnetic film. And then we may have complicated structures below and after that are required and are engineered in order to have a good control of the grain size, the structural interfaces, the temperature stability, etc., etc. So I'm not going to go into too much detail here. I just have to show this as an example. And then on the other side, we have the third generation of GMR of MR materials, which are the tunnel junction devices, where we have here, we look here again, the two ferromagnetic layers, cobalt iron based electrodes, and then in between we have an oxide layer, which is can cross through the top to the bottom or bottom top using the tunneling effect at room temperature. So this is the base stack, and I'm not going to go into too much detail here unless necessary for you to understand how this behaves. What they have in common is they have a spacer, either a copper or a tunnel barrier, oxide, but then they have the free layer, which is our sensing layer. And then they have both of the structure, they have a pinned layer, which is a reference layer to be used as a reference when we monitor the angle of the free layer. And this is how the sensor should work. So the variation in the resistance of this device, according to an external magnetic field, is monitored as a function of the angle that the magnetization of the free layer does with the reference layer. So this is a concept from the magnetics perspective, and then we need to be using this to create a sensor. And what is a sensor? A sensor relies on a linear transducer between some entity. In this case, is the external magnetic field H. And then the resistance changes linearly in a certain range, linearly with the external field. Of course, if the field is too strong, either positive or negative, so here positive or negative, we have the sensor saturation. So the resistance of the sensor does not change anymore here and there. But then we have an operation range, which is the linear range for the sensor to be properly working. And then this linear range is the area that we can definitely optimize according to the applications. And what is the core knowledge that we should have here? We should maximize always the minimum and the maximum amplitude for the resistance. So this variation should be as large as possible. And this is actually the magnetoresistance. So it's variation in resistance normalized by the one of the resistance levels. And of course, this requires a good knowledge on the magnetism. There are several layers here. We have not only one magnetic layer, but we have 3 or 4 or more magnetic layers, magnetic thin film layers that are integrated in the magnetoresistive stack. All of them, since they are thin films, they all interact with each other by proximity. They also interact with each other by interface couplings. So we have to understand how these layers interact and quantify these couplings between at interfaces, at bulk, etc. And we have a good knowledge, and this is something that a student can carry on in a master's degree. They can easily understand what is the coupling between all these layers and then integrate them in a simulation program that can be done for a certain shape for the sensor, and then compare with the experimental results obtained in the real films in the laboratory. And then what is the core, the difficulty here is how can we have a linear sensor? Because if you look at a magnetic material, a ferromagnetic material has a square loop, so the square characteristic. So how can we get rid of the coercivity of the hysteresis? How can we have a linear transducer instead of a square transducer? So all this requires strategies to control the angle between the free layer and the reference layer. And I'm not going to go into detail for all of them. I will describe merged in my next slides. I will describe some of them, but essentially there are several, there is a good knowledge on this topic. And we have actually a revising paper where we have across all these strategies that enable to create under specific conditions to create linear responses for essentially all magnetic stacks. So what are we measuring and what is the meaning of the magnetic range that we are feeling? So if you look at magnetoresistive sensors, they are very interesting in the market. Why? Because they can measure relatively large fields, so 10 to minus 2 Tesla, but also can go to minus 10 Tesla, 10 to minus 10 Tesla. So this means that they are interesting because they can be tuned to span a large area in the scale of fields. But of course, if we want to extend further the detectivity, and we always want to go to the limits in everything in all technologies we do, we definitely would like to explore, to go extending the ultimate limits for detection for these magnetic sensors. So this is one area where I have been working intensively in the past years. Why is that? Because when we use a sensor to measure a signal, if we are in the lab, we know exactly what is the signal, we know the output we expect, and we use it to calibrate. However, if we are blindly in an unknown environment, we never know what to expect. And maybe our noise, when we measure the signal, maybe something like this. We have some oscillations in the resistance of the sensor, but how can we know that these large peaks are signals and not noise? And if now we have a smaller signal, and in this case, this experiment is an example. If you want to have a loop around a current loop around the sensor, you just create the magnetic field by changing the current in the loop, and then you can set to have 140 picotesla, for example, and here you can see that you can read some signal out of the noise. Then if you reduce the magnetic field by reducing the current, then you start to have some doubts. What is the signal actually? I cannot really see signal because it could be noise, I don't know. So this is actually the limits where we are, and it's very interesting when you start to really using your sensor for an application. It's very important to have to ask this question: how can we know that we are actually having the the optimum signal to noise ratio for the application we have. And in this case, we need to distinguish. And signal to noise ratio is if we have large signals and low noise, no problem. If we have large noise, we should also have large signals. Otherwise, you cannot measure anything, and all the signals are masked here in the noise. So ultimately, we have the signal to noise ratio should be 1, and this is the ultimate limit for us to be able to distinguish any signal out of the noise. And again, another important factor here is the signal and the noise may depend on the frequency of operation. And this is another factor that normally an inexperienced engineer does not account. So if we are going to measure the brain activity, for example, or the fields, magnetic field in a current device, for example, we always expect the same sensor should work in both scenarios. No. They will have to be tuned also for the frequency of operation. And why is that? Because if you look here, this is a academic graphic where we have the noise voltage, the voltage noise for an electronic device, any electronic material, that always have these characteristics. So we have, for low frequencies, we always have a larger noise, and then the noise decreases linearly down to a certain frequency, and then it starts to be flat. And this flat is what is called the shock noise and the thermal noise. And it means that we have this is actually this is depending on the temperature and the intrinsic resistance of the material. But then the 1/f noise, and this is a very important region of the noise spectra, can be a killing factor for the applications. So we have been working on low frequency applications. Normally the biomedical applications, they work in low frequency. So our heartbeat and our brain activity are always running less than 10 Hertz. So, or reducing the 1/f noise characteristics for the sensor. So in order to have this in mind, we have to recalculate our field detectivity. So let's look at the signal to noise ratio. We want in the limit to be equal to 1. So signal equal to noise. Let's look at the signal. So the signal here is the voltage decay linearly with the magnetic field, assuming that we are out of saturation. We have the noise, voltage noise. We know that we have 1/f dependency down to a certain frequency. So we have to have the signal equal to the noise. So this is the equations that are simply describing the signal to noise ratio parameters. And here, this is where we are going to use in the next slides to tune our device. So we have several factors that we can play with. We have the delta H, so the field range, so what we call the linear range. We have the magnetoresistance. We have this phenomenological constant, which is what we call the Rouge constant. We have the area of device and the frequency. So we have some parameters that it seems easy to have controlled in order to have a good definition for the signal to noise ratio. So we have to optimize all these things simultaneously in order to have the optimum detectivity. So let's start with one of them. So first, if we have if we can avoid the frequency 1/f, everything will be perfect. So instead of working here in the at low frequencies where we have the larger noise, why can't we shift the operation of our sensor to larger frequencies? Yes, it's possible to be done, and there is several works that were reported in the past years where people were introducing modulators here in the cantilevers, normally cantilevers, where we have a magnetic signature, and this magnetic signature will modulate the external fields into, which is almost DC, will modulate it to a certain frequency, and then the sensor that is here in the red region, the sensor will receive a net magnetic field that is oscillating in higher frequencies rather than the DC field that is in the environment. So this strategy works quite well, but it again starts to be complicated. So we are initially expert in doing magnetic sensors. Now we should also be expert in doing MEMS integration. So the process starts to be complicated. And we need to accept, if we need to use this strategy, we need to accept that the magnetic sensor integration is not just gluing a sensor in our PCB or chip carrier. Then magnetoresistance. So, how can we improve magnetoresistance? Yes, here is a very interesting area. I'm not going to go into too much detail, just to locate you a little bit on the history from the past. So when I started my PhD again, I started in a very exciting time. I started working with aluminum oxide barriers here in 1997. So it was here in my time. So everybody was very excited to have tunnel magnetoresistance at room temperature. And I did myself work in the aluminum oxide tunnel junctions, and then suddenly people also found out that there are other options that could potentially lead to much higher magnetoresistive ratios, and these were texture and crystalline materials that would have coherent tunneling between the states from between the two electrodes. Magnetic electrodes. So comparing with an amorphous barrier, which is the case for aluminum oxide, the MgO barriers looked much more promising. And in fact, they could very rapidly, so here in 3 to 4 years, people could demonstrate from 0 to 600% magnetoresistance at room temperature. So it was quite exciting. And in fact, this is what people use now. So I must say that this 600%, which is not observed in sensor, is observed in stacks, in multi-layers, but not with a sensor linear characteristics. In a sensor, as far as I know, the maximum magnetoresistive ratio that we have now in 2022 is around 220%. So somewhere here, but we are here in 2022. So this means that there is a lot of work that still is required for a sensor to operate. So we have good magnetic materials, we have a very good tunnel interface, we have a good control of the magnetic properties, and then at the end we provide a sensor that changes the voltage as a function of the magnetic field. And here is an example of an experimental result from one sensor that shows a tunnel magnetoresistance of 166% using MgO barrier. So this is an example that can be achieved in the lab, normally at room temperature, and this is a standard value that is normally obtained currently in very large number of labs actually. Another strategy was to increase the area. Okay, so here increasing the area. So let's increase the area. And this is an example. I'm sorry for the density of this slide. So let's look here at the geometry. We have here one sensor. The sensor is should be micrometric dimension. Let's increase the area to 26 times 26 micrometer, diameter 20. And if we increase the area, then 26 micrometer is a large sensor. We see that the signal starts to be improving with the area. So here, this example shows that we can detect around 50 to 100 picotesla at low frequencies with these sensors. But still, let me remark again that 26 micrometers is a large device. Another strategy is, instead of just one pillar with large area, where the magnetic response can be difficult to achieve, is many times easier to have a sequence of several tunnel junctions connected in series, each one with a smaller area. So this means that each one will have a very well controlled linear range, easier to control, but then we add several of them, and in global they will have, and in this case is an example with more than 1,000 MTJ. So each of these squares are MTJ, TMR or MTJ devices. So we have more than 1,000, and if we have more than 1,000, then we can still maintain a large output response, and this will be favoring the noise response at the end. So if we then control the detectivity, so the minimum field that we can obtain, the minimum field should be as low as possible here. We start to see that if we want to have lower detectivity, so detecting lower fields, we should always go to large areas. So the tendency is not to go to small areas. So it's always difficult to go to small areas without compromising the detectivity. So what is the message here is, again, if you want to have small devices, we cannot achieve the minimum detectivity. So the field is always around 10 nanotesla. And if you want to go to picotesla, then we should really do other strategies, but always increasing the size of the device. And one example that, and one work that we have done recently was when we say increasing the size of the device, we are piling up, we are adding up together sensors side by side in a wafer. So we have one sensor here, we have the transfer curve, and then if we want to save space, why not to put them piling up vertically? So this is a good option to save space. And since we are putting them vertically, why not to put them vertically and then also in series in serpentine? So X, Y, and Z and devices piling up laterally and on top of each other. So this is what we have done. And we have here the individual, the result, this is individual transfer curves. This is the resulting transfer curves. And here is the resulting for the series of vertically packed spin valves sensors. In this case, this is a GMR, it's not a tunnel device. It's a GMR because it's fully metallic transport. It's easier to build. So it means that we have done this and we could bring the noise down to picotesla at room temperature. If we have a large number, so everything can be simulated. So these results could be simulated before the experiment is done. And the idea here is to measure, and we could measure picotesla, so 800 picotesla at low frequencies in a randomly noisy environment. So it's not a shielded room, it's just a noisy environment where the sensor is there just in the middle of all this noise at room temperature. So this means that if we want to decrease the noise and to increase the signal to noise ratio, there are always strategies that requires your imagination and the capability to build them in the lab. Then an obvious strategy is to reduce the linear range, so to have more and more and more sensitive devices. Of course, we can think about adding flux concentrators. So this is a strategy that is very old and very well known in industry, actually. So if you want to enhance the field, you just have to focus the field that comes from outside the external media through very sensitive with high permeability magnetic materials. And then they will concentrate all the flux of this magnetic field, concentrate it into the region of the sensor. So this is a cross section here and a 3D vision. And the sensor is here in the middle, and we have the flux concentrators on top that helps to enhance the magnetic field. And this is an example. If we have a simple spin valve or GMR sensor, the transfer curve will have this very nice linear response. As soon as you start to concentrate the magnetic field from outside, you have a really sharper sensitivity. So this is a very efficient way to focus the field, and we have done this for GMR and also for TMR. And one important parameter here is how to do this without occupying a lot of space. Because if you look at the sensor is here, These are the contacts laterally. But then if you want to add this extra magnetic flux concentrators, everything takes space. So your device is always doubling the size. The footprint is always increasing. However, if you can increase your sensitivity by a factor of 100, which is what we see here, gains of 100 times in sensitivity, then it's worthwhile to sacrifice a little bit the space. And this is what we see here in more complex structures. And we have here less than 100 picotesla measure for one TMR device. And here we can compare with a 7 picotesla with a spin valve device integrating a complex structure for focusing and refocusing the field in the sensor region. So these are always strategies that are followed, and these are integrated at industry level. We can also simulate the magnetization distribution here in the sensor region, and also the magnetic flux profile near the vicinity of the sensor. So I'm not going to go too much detail here, just to tell you that there are other strategies that save a lot of space, which is to increase the sensitivity. And here we have an amazing high sensitivity for the sensors and magnetic tunnel junction with the MGO barriers. We can just change from a square response to a very sharp response simply by reducing the thickness of the free layer. So if the free layer, this is the same for any magnetic material, if you have a thick magnetic material, it becomes like a ferromagnetic. So this is what we see here in the left curves. So it has a squarish-like curve, it has a hysteresis. But then if you start to reduce the thickness, you start to have either a discontinuous distribution of the magnetic atoms, and also you start to have a perpendicular orientation. So they start to be able to be sensitive to out-of-plane components as well. So this is a combination of effects, and essentially if we start from ferromagnetic to paramagnetic regime, which is we see here in the green curve. Certainly, we have curves that have out of hysteresis, so they are just simply linear, and they are extremely sensitive. So this is interesting to see, and this is a very good strategy to increase the sensitivity of the sensor and reduce the linear range. What is the drawback here? If we measure the magnetoresistance, so TMR, tunneling magnetoresistance, as a function of the free layer thickness, and here we go for the normal is 3 nanometers, so 30 angstrom. Here we have the maximum, 200%, typical. But then if you start to reduce, and you start to have a very nice linear response below 15 angstrom of cobalt iron boron, then you start also to reduce the TMR ratio. So you're losing signal. So although you gain in noise, you also lose signal. So at the end, it's a trade-off between these two effects, and we need to recalculate if the gain in signal to noise ratio is worthwhile when we look at the TMR drop that we have if we reduce the thickness. So finally, going to the Rouge value. So the Rouge value is a parameter that fits and appears just as a phenomenologic number that helps to fit the noise spectrum. And here there is a lot of work done in the past years, very systematic, comparing different barriers, different values from companies and from everywhere, and people use this as the factor that nobody can control, because we don't know exactly where the Rouge parameter comes from. We know that it's there, and if we fit, this is the free parameter that we gain. So at the end, if we change geometry, materials, and whatever we want to change, at the end, the comparable factor between everybody in the world happens to be the Rouge parameter, at least in a certain community. So here we have been comparing, and we are adding up a lot of points here in these curves, where we want to have a low resistance device, and we know that this reduces the Rouge parameter, but also we want to have small area devices, and we want to reduce the Hooge parameter. So I'm not going to go into much detail here. Just want to say that if we assume that the goal is to reduce the Hooge parameter down to minimum values, people are working here so these are the reported dots, and I can tell that these color numbers here are values that we have been obtained in the past 1 to 2 years, and we are reaching values on closing to the 10 to minus 10 micrometer square. So this number is just a popping up number, so I don't expect you to fully understand if you are not expert in this area. The message I want to say is that if we want to optimize materials for the next generation of sensors, we need to be able to find where to change in the full stack, in the materials or in the geometry, where have we the power to change this Hooge parameter. And it turns out that we need to look at different materials. So going away from the traditional nickel iron or cobalt iron boron, and people are looking, and we are also on that family, looking at different materials with the softer magnetic properties, but also with the high magnetization. So this is very important for the signal to be relevant. So this is just to say that, from the material side, there is a huge range of values that can be operated to help us optimizing the sensors. And at the end, what matters is that each of us, when we go to a different specific area and have to design the sensors for a specific end use, we need to know that there are options that we could follow, but we don't need to follow them all at the same time, because they probably will not fit and will not solve will not solve the same problem simultaneously. So we need to be able to adapt each of these physical properties according to the end use. I'm going to show you some examples, and please interrupt me if I'm extending too much my time. But what I selected here is some examples, good examples that highlight how the magnetic sensors have been showing up in the community and in the market as well. So here, this graphic was presented in a roadmap that IEEE Society produced a few years ago on the magnetic sensor footprint in the technical and scientific community, not magnetic recording, so not hard disks for computers, but everything else. And here the technical readiness level, so shortly the TRL level, so 9 means that is already sold in the industrial level for a customer. 0 and 1 means that 0 is not existing, but 1 in low TRL means that they are still in the development, in fundamental research, and so on. So as soon as you start to increase the technology readiness level, it means that we are ready to reach the market, at least in some way. And we can see from the timing here, we have several products appearing here where the magnetoresistive sensors appear. So I selected here this application, so you see the title, non-destructive testing and monitoring. So this is for control. If you want to use magnetic sensors to control surface quality, monitoring the state of infrastructures, the state of magnetic fields from a tool operating. So all these require magnetic sensors, and actually the TRL level is quite advanced here, and we have for sure several systems here in the application case that are reaching the market, at least for a low scale production. And in that case, I can provide you some examples how can we integrate a sensor in a non-destructive test for quality control. For example, if you look at eddy current, the tests, and this is a very interesting market for quality control in industry. So if you have, for example, for the winds for aircrafts, or for example, if you are doing welding for joints in the metallic foils or metallic plates, or if you have pipes in the nuclear facilities, for example, it's very important to understand if there are scratches and holes and fissures in the welding joints or even in the material itself. So it's very important to measure the eddy currents. There are methods to measure the eddy currents. However, they are not so sensitive as the magnetoresistive sensors. The magnetoresistive sensors are able to detect discontinuities in the magnetic field created by the eddy currents in a surface. And this can be done with the scanning of using a large array of sensors. In this case, we have here the sensors here in this surface, and then this is interposing electronics with the ASIC, where we have the multiplexing and the amplifiers, etc., to read out the individual sensors and then do the classification of the signals according to the surface that is inspected. So integration with electronics is a very powerful capability that magnetoresistive thin film sensors have. It's very easy to find ASIC electronics and then on top of it build the magnetoresistive thin films and process them so that we can use the integrated electronics with multiple sensors simultaneously. This has been used, for example, for other scanning and control applications. For example, for surface inspection in coins or in paper bills and ATM machines. Actually, for all ATM machines, we have allowed not only the optical detectors, but also the magnetic detectors. And we are proud to say that we are selling magnetoresistive wafers with sensors that are integrated in these large arrays for ATM machines in a Chinese company. So our sensors are in around the 5,000 machines, ATM machines in China. And then in a more detailed and cryptographic way, we have been using these magnetic sensors here. This is a nice chip integrated in a reading head that scans over information that is written with printed magnetic ink. In this case, we are showing here visually the scanning of 2D barcode, so nothing special. This can be also done by optical laser detectors. However, what happens if you change and rotate the paper and you cannot have optical access? The sensor can read it anyway. So this is a very interesting market for security label and track and trace applications. So we have been working on this. And we are supplying sensors for companies, for actually one big company working on this market. So there is a constant need to have people, and they are hiring, having people with the know-how to optimize sensors and integrate them in smart applications. So this is quite important. It's not just material, but understanding how the material are being used. And then a very rich market is the Internet of Things and the smart grid with energy monitoring. So more and more, we are replacing the power and the electricity by new sources. And these new sources need to be monitored constantly, because it's important that the renewable sources are integrated in the power grid, but they have discontinuities in the supply. For example, solar power only works during night, so it needs to be stored during the day, so that at night it can be used. And then the levels of replacement and the levels of usage needs to be continuously monitored. So it's really a boom for magnetic sensors, is to have integrated in all devices that have smart meters, renewable sources, batteries, integrated batteries, etc., etc., etc. So this is a really interesting market that exploded in the past years with the magnetic sensors requirements. And this is an example how the magnetic sensors are integrated. So this was how they are integrated 20 years ago. We have a power grid, and then the sensor was put outside this the cable, and we can see even here the wires. These wires are needed to read the sensor. So this was actually 25 years ago. Now the sensors have their own electronics. So this is how it looks like. They have their own electronics. They have here a radio emitter, and everything is placed locally outside the cables, and the signal goes outside automatically wireless to the station, so that each sensor can provide real-time information to the central, and we don't have wires and cables, additional cables and wires there to read out from the sensor. So this is quite interesting, and we have been working with several different companies with different approaches related with current sensors. Essentially, we may integrate the sensor with the current itself from the grid, or you can do it remotely in an open loop configuration. So these are examples on how the sensors should appear. And our magnetic sensor is, if you look here at this design, magnetic sensor is just a small element here with 3 millimeter square. We don't need more for the magnetic sensor. Everything else is electronics. And the same here, we have the magnetic sensor and everything else is electronics. So, and this is an example where we can put the sensor here in the power meter, and inside this box we can integrate a transmitter, processing unit, and everything can be then monitored on real time. We can plug in here our refrigerator, for example, and we can monitor on real time and send to our mobile phone our consumption in terms of each electronic device can be sending its own consumption, so that we can monitor and control this in real time. So this is actually an interesting application that is explored, I think, from in Portugal, from the National Company of Electricity. They are exploring this already to monitor the consumption in the devices. But so this is just to say that there is a large growth in the needs for electrical sensors, and this is expandable always to all electronic devices. Everything is now electronic. And all of these devices require magnetic sensors, and we cannot avoid them because they are the best current sensors that we can have. And then especially because they're also small size and can be easily integrated with the external electronics. So what we want to do now is to make sure that we reach these markets, and those that are doing experimental research and more low-level research, or TRL levels, less advanced, so more fundamental, we all understand that with some push, maybe these sensors can be easily integrated in very advanced applications that our daily consumer would use. So I think I'm not sure if I have time for more applications. Can
a couple of minutes maybe? So
okay.
Just to close.
So maybe so maybe I will jump here to biomedical applications. I'm sorry for this. I'm going to focus now on the what I think is my favorite application, which is the position sensing and human computer. So basically, so physicists do not interact directly, so it's not a straightforward collaboration. However, we have been seeing several interesting ways to introduce to robotic applications to magnetic sensors, and one of them is in humanoid robotics. Although I'm not going to talk about industrial robotics, I'm talking about humanoid robotics and precision robotics. Here, for example, if you look at one hand, maybe I can challenge you for next time you look for robots. You ask them, or you try to see what happens here in the joints of the fingers, how the angle is controlled in real time. So in most of these fingers, they have between each two phalanges, they have a magnetic encoder. So they have an angular sensor, so magnetic sensors that detects the rotation of the small magnet that is on the other side. So it's sensitive to understand what is the angle that each joint has during the grasping of objects. So this is very interesting, a very interesting area. And the issue is all these sensors that are integrated in robotics, in most cases, they are not state of the art. They are just commercial sensors that robotic people found out. So this is a good market for those that are doing research, because the commercial sensors normally they are larger than they should be. And if you do research and you go to the robotics people and have access to the finger, then we can do miniaturized devices. And this is what we have been trying to do here. We have been trying to follow to cover the phalange skin with several sensors, and then from here try to understand when we press the surface of a textured surface, we could understand what is the topography there. And here is an example reading Braille. So these are bumps in the surface, and this was done actually together with our colleague Quazel in KAUST. And we have these artificial cilia that are magnetic. And here on the left side, you can see the same strategy. And if we move this and bend this cilia, we could detect some fringe fields in the sensor that is located below. So I'm not going to go too much detail here in these areas. I would be more than happy to share with you some references for you to follow this from the application side. I'd like now to summarize the last minutes. So essentially, my message is we found at the moment several mixture of terms. So you may find people calling spintronic sensors because people are allergical to old magnetic sensors. You also find people that only calls them magnetoresistive sensors, and there are people that generically calls magnetic sensors, and magnetic sensors means spintronic sensors. So essentially, this means that we have a wide variety of users and at different levels, not only in the market, but also on the research level. And you can find naturally magnetic sensors and spintronic sensors in a wide variety of applications. Then, if you look at these applications, you see that they are quite advanced, and they are in our daily life devices. We can see several products like ATM machines, handlers for pick and place machines, biomedical devices, etc. There are always challenges, and the challenges I did not focus here. I did not mention the thermal stability and the cross-field immunity. So what happens if we have fields from other directions interfering with our sensor? So this is interesting to address as well. And also measuring very low magnetic fields. I focus a little bit more on this area. But in following all this, so I would say that the message, global message is it's very, 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 very important that the role that research institutes are having now and universities are having in the training of the next generation of engineers. Because although all these technologies are well known in the market, and this sometimes is a drawback for attracting new students. So I see, for example, in my case, that sometimes I cannot see spark in the eyes in the younger students at university, because they are following from probably some, for example, looking at the graphene when it was the era of graphene, or they look for photonics because they were happier to see a flashy recent result on that area. So differently, the spintronic sensors are quite mature, but still have very, very, very interesting challenges. And the companies that are using these sensors for 20 years are now going back to the research and to the fundamental understanding of these devices, because there are unknown problems that remain to be solved. So they rely on us as research institutes, as academics, to provide them creative people to see all problems with new eyes. I think this is what we have to do at all levels in our activities. So this summarizes my talk. Thank you for staying there and listening until the end. And I will be very happy to provide you more information about everything and that I do, and to communicate more with you if you need.
Thank you. Thank you, Susana. This was a really interesting talk. I really enjoyed your presentation on the different aspects of optimization on GMR and TMR based sensors. I would like to open the session to question. I have a few questions for you. I suppose that there is also some question in the conference room. I will start.
Sure.
You mentioned in some slide that you have sensor based on MEMS too. That in that area, you also have on top of your signal noise, you have your mechanical noise due to the MEMS. So do you recognize it, or can you recognize it and treat it separately, or how do you analyze the noises coming from?
Actually, we never worried about the mechanical noise from the MEMS because MEMS were so the idea of the MEMS was to modulate at a specific frequency. And these frequencies are relatively small for MEMS, but are large enough for the magnetic field to be to have to get out of the 1/f region. So in fact, the MEMS noise was never the problem here. So the problem was to extract magnetic signature and to reduce the magnetic noise for magnetic signal.
Okay, understand. Also, you have in some slides you show the fabrication of some flux guides to concentrate the magnetic field of the TMR. I'm really impressed for the shape of the contact. You have like a triangular shape.
Maybe this one, right? Or not?
Yeah. Why is the shape of that, of the contact of the flux concentrator?
Actually, maybe I don't know. But, maybe this one. Maybe this one, right?
Yeah. In that
maybe
one.
This one. Yeah, here we have. So the idea here is to have a round around the tunnel junction. So the TMR sensor was round. The reason of the being round is to have not to have an anisotropy, so to minimize the magnetic domains trapped in the corners. And then if we want to have this, then the idea is to put the flux guides following this circuit. So I see here that this is very irregular. So this is not a smooth angle here. This is because of the lithography limitations when this was done. And also it was simulated to have these small edges here. So to trap here the magnetic domains of the flux guide itself, so that it has a smooth performance along the full range of the linear field. Okay, we have actually here on the front. Where do I have it here? Here on the front we have so typically a flux guide has this shape, so either flat or if you do it better, you have a trimmed edge, correct? So this is what normally we expect to have from a flux concentrator. In that case, the issue was we were having the round profile here in the sensor. So it was not so easy to have a sharp, and we don't want to have different separations. So we should have also a round profile for the gap. It's not usual, and normally we don't do it like that actually. Okay.
Another question: how about the yield of the devices on large scale? Because you also in your lab you can fabricate thousands of devices on top of a wafer.
On a wafer.
Yeah. Have you analyzed the yield of that?
Yeah.
How do you do it?
Yeah, this is a very tricky question. So normally we never like the answer here. So I'm going to be very honest. So if we do AMR or GMR sensors, the yield is more than 90%. So all sensors work. meaning that they all have electrical contacts, they all have the magnetic characteristics that were specified. And in some of them, normally in the borders, we may have some irregularity and somehow a lower magnetoresistance or some other defects coming from the microfabrication process. If we go to, and I'm talking about 6-inch wafers, so 150 millimeter wafer. So all sensors in the wafer work. If we go to TMR, the yield is much lower. Okay. And it's very difficult to have. And the yield then, for TMR, the yield is measured in three ways. So the first difficult issue is to have contact to all sensors, so to have electrical contact. Normally the electrical contact, we don't have 100% yield, we have 85, actually 90% yield in the electrical contact. Then the difficulty is to have a nice linear response. And the yield in the sensitivity, so the slope within the specification, so the yield is much lower. So normally we have between 80 to 85% of the sensors that have the proper sensitive slope. So this is not so easy. And sometimes, if the process goes wrong, we may have, for example, in a batch of 20 wafers, we may have 5 of them that do not work at all. Because during the etching, the process for TMR is much more complicated than for GMR. For TMR, we have several lithography steps. If we have double contact, normally this is what the industry requires. So from these 7 lithography steps, there are 2 or 3 that are high risk. And sometimes if we fail one of them with low yields, then it propagates to the full wafer, and then we have a wafer that is almost no functional. So the TMR is really an expensive technology, and it's expensive to have a high yield and provide a reliable number of wafers, one after the other. And also because if you look at the TMR, and I think you may know this well, if you look at the TMR sensor, the resistance, normally the resistance is a specification by the supplier. So they ask us, you need sensor with 1 kilo ohm, 2 kilo ohm, 2.2 kilo ohm. They do the same for TMR. And the resistance in a TMR sensor depends not only on the geometry, but depends dramatically on the thickness of the tunnel barrier. And here we are talking about tunnel barriers that are 1 nanometer, 1.1 nanometer MgO. And if in one wafer we have from 1.1 nanometer to 1.15 nanometer, so half an angstrom in average, yes. This can increase 1 order of magnitude, the resistance, yes. Or decrease 1 order of magnitude. So this is actually a killing factor most of the time with the TMR wafers.
Yeah. Okay, thank you. For my side, I have one last question that it actually is in my mind for the last couple of months. When you fabricate device for sensor or for MTJs, you can do it using 4 probe contacts or 2 probe contacts. But in large scale wafer, you also use 2 probe contacts. This is only for saving space, or you don't?
No, it's saving space.
Okay.
Yeah, normally saving space. So for tunnel junctions is always saving space. So it's 2 contacts. For spin valves, normally, whenever there is space, we try to use 4 contacts. But normally, for the devices for industrial applications, normally it's always 2 contacts. And also because the sensors normally they are not integrated alone; they are integrated in a bridge configuration. So here I show results for individual sensors, but normally in the wafer we have each chip has to have the full bridge. So it should have 4 sensors and 2 of them rotated in a different direction. So everything occupies space. Yeah, that's okay. Right.
Okay, thank you. Those are my question. I think there is a question in the conference room. Carlos, you can go ahead.
Hola Susana, hermosa charla. ¿Me entiendes el castellano?
Yes, sí, sí,
Okay.
compreendo.
Bien.
É melhor falar em português.
Okay, well, probably I'll follow in English. I don't know what to ask you, but I'm surprised all the things you do. Do you have a large sparring there in Portugal or in Lisbon, or what is the machine you use, or you send things to a foundry?
No, we do
No.
it here. We do here.
No.
We are Portugal. Portugal is deep Africa, so we need to do it ourselves. Otherwise, everything takes time. But for the deposition, definitely we do it ourselves. We have these are three sputtering tools that we have. Fully dedicated to thin film for spintronics. Of course, we can also have other targets installed, but we have, for example, this small tool. This was the sputtering tool that has 6 targets. The wafers are 4-inch. Then we have this the other machine with ion beam. We have 7 targets and 6-inch wafers. But then runs batches of wafers, so it's not one single wafer, it's a cassette loaded. And then we have another big machine that also handles 200 millimeters, so 8-inch wafers and 12 wafers per batch. Actually here, this is not updated, we upgraded this machine the last 2 years. So during COVID, we received one extra model for this machine. So we have 8 more targets available in the same tool. So the number of targets is quite important. And if you look at this, so AMR, you just need 2 targets, you don't need more. GMR, we may need 6 targets, 7 more maximum. But if you go and look for the TMR, the structures are being so complex now that we easily end up needing 9 targets, 10 targets. With the buffers and cap layers and heavy metal in the middle, so tungsten there and so on. So it's very important to have more targets in the same vacuum tool. Yeah. But we do it everything at INESC. We have these sputtering tools for large wafers, so we handle 200 millimeter wafers, and we can do the lithographies and the etching and the metallization, everything in 200 millimeter wafers. And this is what we sell to our clients. We do a lot of production, small scale production, of course, because we are research institute, but we do a lot of prototyping with let's say 50 wafers, 100 wafers for per year for other customers with these materials.
Okay.
Nice.
And I don't know. What's the limiting problem that you had with these big sputtering machines? I mean, you can do a good vacuum to begin with, or what
yeah,
is the...
For these tools we have so the vacuum is 10 to minus 8, so 1, 2, 3, so low 10 to minus 8 torr. So this is the vacuum that we have. So it's not so small as MBE, for example, but it's okay for MGO. 10 to minus 8 is sufficient. So the critical part here is cross contamination. So if in the sputtering in sputtering tools, the targets get eroded. So as soon as you start using a target, the target gets the profile changes and the deposition rate changes with time. So this is a problem if you want to deposit, for example, the multi-layers for tunnel junctions. We have a 0.65 nanometer thick spacer. So we don't have just we don't round to nanometer. We round to 0.01 nanometer. So this precision can only be achieved if we have a continuously monitor of the target usage So the target, if we have every 3 months, 4 months, the deposition rate changes. So we have to have this in consideration.
Okay. Well, and what about the link with industry? Do you happen to, I mean, do you work on demand or
Yeah,
how's
so
that
so it happens that since I was a PhD student, I was always used to work with the companies. So from time to time, we have people approaching, companies approaching in ESC. And then they will ask us, for example, in the case of materials, they want to evaluate, for example, instead of manganese iridium, they want to evaluate manganese nickel. So a different material. And it was easier for us to replace one of our targets and then to do, this is an example of a collaboration with the industry. So they send us a target, so they pay for the target, and then we install the target in our machine, and then we just do a series of samples with their material. And if the results are good enough, then they will consider buying the target for their production line. So this is an example of collaboration because we were fast in assessing the quality of the materials. Another example is we have companies that approach us, and this is happening recently in the past, I'd say 4 years, since 1918. We have companies approaching us. They have products in the market already. So they are selling current sensors with AMR or GMR, and now they want to do TMR. So they don't have any experience in TMR, but they want to start having their own products in TMR. And it's not easy to find a factory that provides them TMR because they don't have experience. Europe is a small, do not have a large capability for production. So it's not like Malaysia or Asia. So they don't have big options and they don't want to invest in a full line for production of TMR sensors. So they asked us, can you help us with the development? So we help them with the sensor design according to their product. What is the frequency they want to work with? What is the sensor detectivity they want to handle? What is the size that the ship should take? And then we help them to optimize the design and the best sensor material. And we produce several wafers for them to test and to assess the sensors. We sell them the wafers. And then from there, they can decide if they would invest in buying us the stacks, and we send them only the stacks, and then they do the microfabrication in their factories, in their production lines, if they have one. Or if they do not have, and they don't need a large number, we can produce them the wafers they need. And for TMR, it's interesting that there are several companies that do not have TMR. They are major players in the market, but they have a large share code with AMR or GMR, but not TMR. And now it's too late to start from the scratch. So it's too late to decide which machine shall we buy, which process shall we have for the TMR sensor. So it takes too long to do it. So they are speeding up using us and similar institutes to develop a process, and then they take over and transfer this technology directly to their foundries in Asia. So this is one way that I see that companies are using our sensors. Another thing is to help them to optimize specific points. For example, for the exchange materials, for the antiferromagnetic materials, for example, they have different blocking temperatures, different thermal stabilities. So the companies we have 2 companies last 2 years. They asked us to help them to optimize the blocking temperature for those materials. And they want to have, because they wanted to, for the bridge, if you want to repin, to create a bridge in the wafer, you need to have 2 sensors in one direction and then 2 other sensors in the 180-degree direction. In order to do that, the cheaper way to do that is to process a wafer with the sensors all oriented in the same direction, all of them. And then with a laser, and a small magnetic field. You go on top of the sensors in the area of the wafer you want. You hit with a laser, and then simultaneously you repin with a magnetic field that sets the 180-degree orientation for that particular sensor. So this laser repinning is a very widely used strategy for industrial partners in 8-inch wafers, so all wafers with more than 60,000 sensors in the wafer. So they should do this to half of the sensors, so it takes a few hours, as you can imagine. But then it turns out that if you want to change the orientation of antiferromagnetic pinned layer, you know the blocking temperature for this material. You can say, for example, manganese iridium is 280 degrees Celsius. So you hit the laser until you reach that temperature, and then you apply a magnetic field. This is perfect, ideally, but in practice, you don't have one temperature of blocking. You have a distribution of blocking temperatures. So in some areas of the wafer, the time that you are using to repin the sensor is not enough. So you need to have more time or more energy or higher field or whatever. So this is a very, very relevant point that the industry is asking us to help. And in particular, working on materials that have a narrow blocking temperature window. So they don't have so much dispersion in blocking temperature. So this is an interesting area that we have been also working with. So there are several ways to do applied research. And another way is, of course, to provide sensors customized for a small production. For example, for this robotics or for the scanners, it's a clear end use. So we just have to provide sensors integrated in the system. So this is something that it's also interesting. It does not make us rich, but it's interesting to learn more on the integration part. And this is very relevant.
Well, thank you very much, Susana. For my questions, it's okay.
Thank you, Susana.
With this,
I would like to thank you for your talk, and your welcome.
I'd like to thank you. It was very nice to see you now finally, and I really hope that we could.
Yeah. Martin Sirena sent his regards.
Thank you.
He left the room. So you're welcome to share your work with us whenever you want. So I hope to see you in the next invited talk. So with this, I would like to finish our seminar of the week, and until the next time.
Okay.
Next time we'll have the talk of Rudolf Schäfer. He's going to talk about the Kerr microscopy. So, thank you again, Susana.
Thank you all, and good luck for everything. And if you've traveled to Europe, if you cross by in Lisbon, please let me know, because we are close to the airport. So if it's just have to go a few hours earlier, and you can visit us. I will pick you up in the airport, I'm sure.
Thank you. Gracias. Thank you.
And so, bye-bye.
Bye.